Hi folks, I hope this video finds you well, and we are moving on with our discussion of rational functions. And today we are going to focus on rational functions and horizontal asymptotes. So hopefully you've already viewed the vertical asymptotes video and have some understanding about those, because today we are switching to horizontal asymptotes. So if you have your rational functions and horizontal asymptote document pulled up, I am going to share my screen and let's talk about some stuff, shall we? All right, so first and foremost, we are starting in Desmos per usual, it seems like. And I already have the first function typed in. So first of all, just to kind of review, this rational function definitely has a vertical asymptote at x equals 2. As you can see, the denominator is x minus 2. And so what you're doing is you're asking yourself, when will x minus 2 be equal to 0? Because that would, of course, be an error. 5 divided by 0 is not possible. And in this particular case, that would happen at an x value of 2. Okay, well, that's the vertical asymptote, and again, that's an error. But horizontal asymptotes, okay, so check it out. If we zoom out, can you tell that this rational function also seems to approach a flattening or like leveling out, so to speak, value in the horizontal direction as well? See, now vertically speaking, we already know that it has a barrier at 2. X equals 2 is the vertical barrier, but there's also a horizontal barrier if you look carefully. Now, you could probably estimate this one just with your eyeballs and say, well, yeah, I think I do see that it has a flattening out of sorts, and it appears to just be the x-axis. So maybe the horizontal asymptote, or where it's flattening out to, is simply the x-axis. And in this particular case, you would be correct. The horizontal asymptote is the x-axis. But I want us to talk about why that's the case. So I'm going to go up here to my, first of all, I'm going to make sure that my mouse is on the very top line where my formula is. And then I'm going to go to the gears and I'm going to add a table. So for vertical asymptote, once again, we know that the value of 2 is undefined. Vertical asymptotes are errors. Horizontal asymptotes are not errors. Horizontal asymptotes are more along the lines of what happens in this function when you look way out into what we call the end behavior of this graph. So what I mean by that is, if you want to know the end behavior of a graph, you don't plug in numbers like 1, 2, 3, 4. You plug in really big numbers. So if I plug in like negative 100 or negative 1,000 or negative 10,000, what you can see is that when I plug in really big numbers for x, my answer is pretty dang small. This answer is 0.05. When I plug in 1,000, it's 0.005. When I plug in 10,000, notice that's scientific notation. So that's really 0.00049. And I could even exaggerate this more. Check it out now. If I plug in, what is that, 1,000,000, I think? 4.9, negative 4.9 times 10 to the negative 6. Okay, so that's 0.0000049. So it's really tiny. And that would happen if I plug in positives as well. Check it out, plug in 100. Plug in 1,000. Plug in 10,000. Plug in a whole bunch of zeros. So again, now I'm on the other side of things. I'm on the positive side of things, but look at my answers. They're still really tiny. I plug in 100, I get 0.05. I plug in 1,000, I get 0.005. I plug in 10,000, I get 0.000. 5. And of course, I'm exaggerating it on this last one because times 10 to the negative 9, guys, that's 0.00000000005. Really tiny. So this table right here confirms what your eyeballs are kind of showing you, and that is that in the long run, way out here in the long run, this function does level out at pretty much 0. So this guy has a horizontal asymptote at the x-axis, also known as the y equals 0 line. Oops, not 9, the y equals 0 line. So let me go back to my home screen. So check it out. Ideally, when we graph these, and I'll go back to my other screen in a second to show you that, but ideally when we graph these, we will be labeling both asymptotes. So we already had our x equals 2 identified as the vertical asymptote, and we would also have y equals 0 identified as the horizontal asymptote for this one. Okay. Now let's go ahead and look at the next one as well. And then I'll share my whiteboard with you and we'll talk about some more things. But first of all, what is the other function? Negative 5x minus 4. So negative 5x minus 4. And on the bottom, what was it? 2x plus 6? Yes. 2x plus 6. Okay. Get everything else out of here. Okay, so first and foremost, just to kind of review from our vertical asymptote conversation, this particular rational function has a vertical asymptote at x equals 3. How do I know that? Well, because the denominator is 2x plus 6. And whatever value makes that 0 will indeed be the error. So I would take 2x plus 6, I would set it equal to 0, minus 6, divide by 2, you get x equals negative 3. And you can see with your eyeballs that that makes sense because this graph absolutely has a barrier, a break at an x value of negative 3. Okay, so that's vertical asymptote. For more information on that, of course, go back and look at the other video. But for now, let's talk horizontal asymptote. So again, horizontal asymptote is not an error. It's just looking at what the graph does in the long run. So notice this graph seems to level out as well. Okay, but is this graph leveling out to the x-axis like the last one was? No, it's clearly under the x-axis. And you're like, okay, well, how much under the x-axis? I don't know. And you can look on this side of it too. Notice the graph is leveling out, right? Just below the x-axis. So this graph definitely has a horizontal asymptote. This graph definitely levels out in its quote end behavior, as we call it. And so to explore this, once again, what we want to look at is what happens when I plug in really big numbers. So if you left your table there like I did, it should have automatically filled in. If not, you just have to go back up here and go to the table. I'm sorry, go to the wrench and then click table. But I already have mine here, so it's already filled in. So look at this. I plug in negative 100, I get negative 2.55. I plug in negative 1,000, I get negative 2.505. I plug in negative, what is that, a million. I get negative 2.5000000, whatever. Pretty much negative 2.5. Let's look if I plug in positive answers. If I plug in positive x values, negative 2.4. Okay, let's get bigger. Plug in 1,000, negative 2.49. Okay, plug in, what is that, 10,000, negative 2.4999. Okay, so notice this one is pretty much negative 2.5. So where this graph is leveling out to is at approximately negative 2.5. So the horizontal asymptote for this graph is at a y value of negative 2.5. And so when we graph this, once again, you'll be expected to draw in, or dot with dotted lines, draw in both asymptotes and identify where they're at. So the vertical asymptote is right here at x equals -3, and check it out, the horizontal asymptote is right there. I've now dotted it in also at -2.5. So that's kind of a crash course on what horizontal asymptotes mean. They mean the end behavior, so to speak, of the curve. Sorry, my allergies are horrible today, guys. And how you discover a horizontal asymptote is by plugging in really big numbers. Now, what we need to talk about next, though, is how are we going to identify horizontal asymptotes without necessarily having to go to Desmos and plug in gargantuous numbers? So I'm going to share my whiteboard with you this time. Okay, so the first function was what? Just 5 over x minus 2. And for the most part, like I said earlier, when you're talking about horizontal asymptotes, you're talking about the end behavior. So it's as if you're imagining what would happen if you plug in something huge. Now, technically, there's no such thing as plugging in infinity, but humor me here for a second. If you plugged in something really, really big, then you would have 5 on top, and you would have something really, really big on the bottom. Now, granted, it is infinity minus 2, but at the same time, I mean, like, really, infinity minus 2, that's still friggin' huge. So think about it. What's 5 divided by something huge? 5 divided by a cajillion is practically 0. And notice on the first function, the horizontal asymptote was at the 0 line. And for the other one, what was the other one? G of x was, what was it? -5x. Oh gosh, what was that? I'm gonna have to go back and look at my little screen for a second. Bear with me. What was the -5x? Oh, -4. Okay. -5x minus 4, -5x minus 4, -5x, here we go, minus 4 over 2x plus 6. Okay, now this one we used Desmos to estimate that it was at approximately -2.5. But check it out. If you imagine plugging in something huge, right? So it would be like -5 times huge minus 4 divided by 2 times huge plus 6. Okay, now think about this for a second. -5 copies of infinity. Okay, infinity is already big, obviously. And now we're talking about quintupling it. -5 times infinity, -5 copies of that huge number. Now, in the scheme of things, since we are talking infinity style numbers, does this -4 really do much to -5 infinities? No. Now look down here, 2 copies of infinity. Okay, well, if I had like a cajillion dollars and you told me you were gonna double it, I'd be like, sweet, 2 times infinity, that's taking 2 copies of it. That's pretty impactful. But plus 6, when we're talking cajillions and cajillions and cajillions here, the plus 6 is pretty much moot. It's just not important on the scale of infinitely huge numbers. So check out what happens here. You've got -5 copies of infinity, essentially divided by 2 copies of infinity. So you pretty much have -5 cajillion. I'm just going to add a crap ton of zeros here. I'm not even counting them, so don't judge me. And you're going to divide it by 2 cajillion. I'm not counting zeros, so don't fact check me on this. But that's pretty much what you have. Well, guys, this isn't a trick question, but are you ready? What's -5 cajillion divided by 2 kajillion. Negative 5 kajillion divided by 2 kajillion is pretty much negative 5 halves. Do you remember where the horizontal asymptote was on this one? It was at negative 2.5. Negative 5 divided by 2 is negative 2.5. The horizontal asymptote for this one is at negative 2.5, aka negative 5 halves. Check it out. It came from these coefficients. That's where the horizontal asymptote comes from. It comes from those coefficients. Now on this first one, let me get a different color. On this first one, you're like, well, but what were the coefficients on this one? I mean, down here, there was just an x. So what's that coefficient? Well, good question. That coefficient is pretty much just 1. If it just says x, then that's like a 1x. And then up here for the 5, you're like, well, what's the coefficient up there? Well, guys, there is no x up here. It's just a 5. So if anything, you could imagine that there was a 0x up there, if that helps your brain. Because if you imagine that there's a 0x up there, well, then you can use that idea that we just talked about, and that is that it's the coefficients, and you can grab that 0 and that 1, and that would also confirm that the horizontal asymptote is 0 over 1, aka 0. So once again, the horizontal asymptote is not an error like the vertical asymptote was. The horizontal asymptote is a value that the graph just levels out to. It's not an error at that spot. It's just where it levels out to eventually in the long run. Notice I'm plugging in infinity because yeah, it takes a while for the graph to actually level out to these values. Okay, so let me clear that and go here. Oh, hello, that's me again. And then let me go to my document now. Okay, so on our document, again, you guys were filling in these tables. Okay, that was your job, filling in tables. And then on the graphs though, here is kind of our takeaway message here. So let me get my little keyboard that allows me to mark up. Here we go. And then I want to have my little drawer. Okay, so on this one, your vertical asymptote was at x equals 2. So you'd have your dotted barrier at x equals 2. And then we also know, so this is at, let's just do this. Y, x, nope. Oh, here we go. Clearly, I am still learning here, guys. All right, so that right there is my vertical asymptote at x equals -2. And then we also, as of today, know that there is a horizontal asymptote at the 0 line. So you would also dot that in. Okay, this is the expectation of what these are going to look like moving forward. So this right here is at y equals 0. That's my horizontal asymptote. And then, of course, where did I just put my pen? Oh, there it is. I'm losing my mind. Of course, the graph itself was, whoa, that's not what I wanted. Let's see. There we go. The graph itself was here and here. And so you just do your best to draw the boundaries of that graph within those asymptotes. It's really, really, really important that you don't accidentally draw your graph crossing right through the asymptote. No, the asymptotes are the barriers of the problem. And so if we do this next one again, the vertical asymptote was at -3. So you would dot in your boundary line at x equals -3. as best you can, of course. I realize mine's definitely not perfect, but that is at x equals -3. And then the the horizontal asymptote we said for this one was at -2.5. So just do your best to identify halfway between -2 and -3 and draw in a dotted boundary line there as well. And oops, where is that? That right there is at y equals -2.5. And then this particular graph was, if I remember correctly, oh, where am I? I lost my thingy. Right. This particular graph was also up here. Careful, careful, careful. Be close to the boundary, but don't cross it. And then on this side, careful, close, but don't cross it. There we go. Okay, good. So you will be in charge from this point on, always, 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 drawing in your horizontal asymptote as well as your vertical asymptote, okay? And then let's get the definition going down here. So let's see if this, whoa, nope. See if this works. Okay, so then we've got horizontal asymptote. And when we say horizontal asymptote, what we mean is the horizontal line that is the boundary or value that the graph approaches in the end behavior is what we call it, or in the long run of the graph. So it's this horizontal boundary line that the graph approaches, but when does it approach it? Way out there, okay? We call it the end behavior for a reason, or in the long run, okay? So it levels out. Now, since we're talking about a horizontal line right now, that's why it's going to always be in the form y equals instead of x equals, like your vertical asymptote was an input value, so it has to say x equals. Well, this is an output value, so it has to say y equals. And then where this comes from, the value of the horizontal asymptote is the coefficients. When we say coefficients, what that means is the number out in front of the variable on the numerator and denominator. So like for instance, let me see if this will, well, let me just switch to whiteboard. That'll be easier. So from this point on, if you have just some rational function like f of x equals something on top, ax plus b, and then also something on the bottom, cx plus d. I'm just making all this up. When we say coefficients, what we mean is the number in front of the variable on top and the number in front of the variable on the bottom. That value, whatever that is, that will be the value of your horizontal asymptote. That right there is your horizontal asymptote, okay? So obviously you'll have a chance to practice this in your homework, and next up we'll talk about how all this applies in like a contextual word problem, but at least for now, you've got the vocab for horizontal asymptote and vertical asymptote now. You know that you're expected to graph them both with dotted boundary lines, and hopefully you know how to find them. Vertical asymptotes, you set the denominator equal to 0. Horizontal asymptotes, you have to look for the coefficient of the variable. All right, thanks for watching, and we will talk to each other soon, hopefully.